Black holes are not black, and they are not holes. And everything you know about them is untrue. Forget about cosmic vacuum cleaners that suck up everything in their path. Forget about portals to other dimensions. Reality is much stranger than any fiction. A black hole is a place where the very logic of the universe breaks down. There, time stops for some and continues to flow for others. There, information disappears forever, violating the fundamental laws of nature. There, the event horizon might turn out to be a wall of fire that will burn you before you can understand anything. Scientists have been arguing about this for half a century. Einstein did not believe such a thing was possible. Hawking proved that holes evaporate. But if they evaporate, where does everything that fell into them go? This is a question that tears physics apart. And the answer to it may mean that our entire universe is a hologram, a two-dimensional projection on the surface of space, an illusion of depth, behind which a flat code is hidden. It sounds like madness. This is the most serious theory of modern science. Before we dive into this rabbit hole, support the channel with a subscription and a like. Ahead of us lies a journey to the boundaries of understanding. And if you are interested in riddles that baffle the greatest minds of the planet, stay with us. We will explore the darkest corners of space every week. Let us start from the very beginning, from the moment when humanity first realized that objects so dense could exist in the universe that even light could not escape from them. This was not just a theoretical mind game. It was a challenge to everything we knew about reality. Imagine a star, a huge ball of glowing plasma, in which billions of thermonuclear explosions occur every second. Hydrogen atoms collide and fuse into helium, releasing monstrous energy. This energy expands the star from the inside, preventing it from collapsing under its own weight. Gravity pulls inward. Plasma pressure pushes outward. Balance is a dance of titans that can last billions of years. But sooner or later, the fuel runs out. Hydrogen burns out, the internal furnace cools down, and then gravity wins. The star begins to shrink. First slowly, then faster and faster. The outer layers fall onto the core. The temperature inside skyrockets to unimaginable heights. A final flash occurs, a supernova, an explosion of such force that it is visible across half the galaxy. In a few seconds, the star throws more energy into space than our sun will emit in its entire life. But this is not the end. This is only the beginning. The core of the star continues to shrink, and if it is massive enough, nothing can stop this collapse. The nuclear forces that hold atoms together break under the monstrous pressure. Electrons are pressed into protons, turning the matter into a mush of neutrons. But even this is not the limit. If the mass is too great, even neutron matter cannot withstand it. Compression continues, and at some point, the entire mass of the former star collapses into a point of infinite density. Such a word appeared in Einstein's mathematics. Singularity, a place where all equations stop working, where the density and curvature of space rush to infinity, where physics ends and something incomprehensible begins. Around this point, space curves so strongly that a trap is formed, a boundary which, once crossed, you will never return from. The event horizon, the point of no return. Beyond it is territory from which even light does not exit. That is exactly why we call them black holes. Not because there is a void there, but because nothing comes out of there. No light, no information, no signals. It is like throwing a letter into a mailbox that is at the bottom of a bottomless well. The letter falls, 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 and disappears forever. The first to understand this mathematically was the German astronomer Karl Schwarzschild. He solved the equations of Einstein's general relativity for the case of a massive non-rotating object and obtained a strange solution. There exists a critical radius inside which the geometry of space is so distorted that time and space swap places. Sounds abstract? Let us try to understand. Usually, you can move in space in any direction. Forward, backward, right, left, but you cannot move backward in time. Time flows in only one direction, into the future. This is an asymmetry we live with. But inside the event horizon, the direction toward the center becomes a direction in time. Movement toward the singularity becomes as inevitable as the flow of time. You cannot help but fall into the center, just as you cannot stop aging. This is no longer a matter of choice or effort. This is a destiny written in geometry. Einstein was horrified by this idea. He believed that nature could not allow such monsters. There must exist some mechanism that prevents the formation of an event horizon, some force that will stop the collapse before everything becomes completely crazy. But he was wrong. Nature not only allows black holes, it produces them in huge quantities. Every sufficiently massive star sooner or later turns into a black hole. In our galaxy, there may be millions of them, and in the center of every major galaxy sits a supermassive black hole, the mass of which is millions or billions of times greater than the mass of the Sun. We observe them indirectly by how they affect the surrounding matter. Gas falling into a black hole heats up to millions of degrees and shines brighter than entire galaxies. Stars near the center of our galaxy rush along orbits at frantic speeds, like stones on a rope being spun by an invisible hand. But the more we studied black holes, the stranger they became. The first strangeness is the observer's paradox. Imagine that you are watching an astronaut who is falling into a black hole. You are at a safe distance, and he is slowly approaching the event horizon. What will you see? As he approaches the horizon, time for him flows slower and slower from your point of view. This is the effect of gravitational time dilation. The astronaut's watch begins to lag behind your watch, first by microseconds, then by seconds, minutes, years. When he reaches the horizon itself, time for him stops completely. You see how he freezes at the boundary, like a sculpture. His image becomes increasingly red. Light loses energy, fighting against gravity. It dims, disappears, but he never crosses the horizon. From your point of view, he is frozen at the boundary forever. Now let us look at the situation from the point of view of the astronaut himself. He falls toward the horizon, and nothing strange happens for him. No stopping of time, no freezing. He calmly flies through the event horizon, not even noticing the boundary. If the black hole is large enough, at the moment of crossing the horizon, he will feel nothing unusual at all. Locally, the space around him is almost flat. Only later, approaching the singularity, will he begin to feel tidal forces, the difference in gravity between his head and feet. These forces will grow, stretching his body, tearing it into atoms. But this will happen later, already inside, and the moment of crossing the horizon may turn out to be the most ordinary moment of his journey. So who is right? The external observer sees that the astronaut never crosses the horizon. The astronaut himself feels that he crosses it without problems. Both points of view are correct. This is not a paradox in a logical sense. These are just two different realities, two different stories that do not contradict each other within the mathematics of general relativity. But physically, this means something crazy. Events happen for one observer and do not happen for another. Reality becomes relative not only in the sense of speed or simultaneity, but in the sense of the very existence of events. For you, the astronaut remains outside forever. For himself, he has long been inside. Both stories are true. Both coexist, but they will never meet, because the astronaut can no longer send you a signal. The horizon has cut him off from the outside world. This is only the first level of strangeness. Now let us dig deeper. What is an event horizon? In fact, it is not a physical surface. There is no wall, no membrane. If you were flying through the horizon, you would not hit anything. You would not feel any resistance. The horizon is a geometric boundary in space-time, a place where light cones, those directions along which light can propagate, tilt so much that all future trajectories lead only inward. Imagine a whirlpool. You are swimming along a river, and the current intensifies. There is a point after which the current is so strong that even the fastest swimmer cannot row against it. This point is an analog of the event horizon, but in the case of the river, it is a matter of the speed of the current against the speed of the swimmer. In the case of a black hole, it is a matter of the structure of space-time itself. Inside the horizon, the direction toward the center becomes the only direction into the future. Any trajectory, any movement, any attempt to break out, everything leads only to the singularity. This is not a question of engine power or rocket strength. Even if you had an infinitely powerful engine, you could not fly out, because flying out would mean moving backward in time, and time never flows backward. This is a fundamental rule, and the black hole uses this rule to lock up everything that falls inside. Falling into the singularity becomes as inevitable an event in your future as the next second in ordinary life. You can delay the moment by turning on the engines, but you cannot avoid it. Just as you can meditate and slow down the sensation of time, but you cannot stop its flow. Inside the horizon, the very concept of spatial direction loses meaning. You no longer have a choice of where to move. There is only one direction, into the future. And the future is in the center. All roads lead to the singularity. This is a geometric fact, not a physical force. A black hole does not pull you toward it harder than ordinary gravity. It simply arranged space-time so that any movement inward from the horizon is movement forward in time. And this is where the real problems begin, because a singularity is not just a very dense object. It is a place where density becomes infinite, where the curvature of space-time becomes infinite, where all our equations give infinities and stop working. Physicists hate infinities. When an infinity appears in equations, it usually means that the theory has broken, that we have missed something. In quantum electrodynamics, there were also infinities, but physicists learned to get rid of them using a procedure called renormalization. They carefully subtract the infinities and obtain finite observable values. But with black hole singularities, this trick does not work. Infinity sits at the very center of the solution and does not yield to elimination. Does this mean that the singularity actually exists? Or is it a sign that general relativity is incomplete? That at very small scales with very high densities, quantum mechanics should turn on and somehow smooth out the infinity? The problem is that we do not have a theory of quantum gravity. We do not know how to combine general relativity with quantum mechanics. These two theories are the two pillars of modern physics. One describes gravity and space, the other atoms and particles. And they are not friends with each other. Their mathematical languages are incompatible. Attempts to combine them lead to contradictions and infinities. String theory tries to solve this problem by assuming that at the most fundamental level, everything consists not of point particles, but of tiny vibrating strings. Loop quantum gravity tries to construct space-time from discrete quantum pieces. But neither of these theories has yet been confirmed experimentally. We cannot look inside a black hole and check what is happening there. The event horizon reliably hides everything inside. This leads us to one of the deepest principles of black holes, the cosmic censorship principle. It was formulated by the English mathematician Roger Penrose. The essence of the idea is that nature hides singularities behind event horizons. A singularity is a place where physics breaks, where causality is violated, where anything can happen. If such a singularity were naked, visible to an external observer, it would create chaos. Events could influence the past, causes could follow effects, but nature is merciful. It envelops every singularity with an event horizon. The black hole becomes a censor that does not allow madness to leak into the rest of the universe. Everything that happens inside remains inside. For us outside, a black hole looks like a simple geometric object described by only a few parameters: mass, charge, and angular momentum. This is called the no-hair theorem. A strange name, but the meaning is simple. A black hole has no hair, that is, no details, no individual features. Two black holes with the same mass, charge, and rotation are indistinguishable. It does not matter what they were formed from: hydrogen or iron, a star or a cloud of gas. All details, all information about what fell inside, is erased. The event horizon is an ideal washing machine for information. Diversity at the input, simplicity at the output. This seems reasonable and even elegant. Nature loves simplicity. But here is the problem. This contradicts quantum mechanics. In quantum mechanics, there is a sacred principle of information conservation. If you know the full quantum state of a system at one moment in time, you can, in principle, calculate its state at any other moment, both in the future and in the past. Information does not disappear. It can become entangled, distributed, encoded in a complex way, but it is always preserved. This follows from the reversibility of quantum evolution. The Schrödinger equation, which describes how a quantum state changes, works in both directions of time. You can scroll it back and restore the past. But a black hole seems to violate this principle. You throw a book into it. The book contains information, a sequence of letters, the arrangement of atoms, the quantum states of all particles. All this crosses the horizon and disappears. The black hole becomes slightly heavier. Its mass increases by the mass of the book, but all other information is erased. For an external observer, there is no difference. Did you throw a book, a brick, or a cloud of gas of the same mass? Is the information gone forever or not? This question turned into one of the main paradoxes of theoretical physics, the black hole information paradox. And attempts to solve it led to ideas that seem even crazier than the black holes themselves. Everything changed in '74 when Stephen Hawking made a startling discovery. He combined quantum mechanics with the theory of black holes and showed that holes are not completely black. They radiate. Slowly but surely, a black hole emits particles and loses mass. It evaporates. This process is incredibly slow for massive holes. A black hole with the mass of the sun would evaporate longer than the universe has existed. But for small holes, if they exist at all, the process can be fast. And here is the problem. If a hole evaporates completely, what happens to the information that fell into it? Hawking radiation, as it turned out, is absolutely thermal, that is, random, chaotic, not carrying any structure. It is like the radiation from a heated piece of metal. You can measure the temperature, but you cannot restore from this radiation information about which exactly atoms make up the metal. The radiation of a black hole is the same. It depends only on the temperature of the hole, which is determined by its mass. No information about what fell inside. So, the information has indeed disappeared, destroyed in the process of evaporation. This was Hawking's own position for many years. He believed that black holes were an exception, a place where quantum mechanics is violated. But most physicists could not come to terms with this. The principle of information conservation is too fundamental. If it is violated, all of quantum mechanics is under threat. A war of ideas began. Some said that information is destroyed, others that it is somehow preserved. But how? If Hawking radiation is thermal, where is the information hidden? Maybe it stays inside in the singularity? But if the hole evaporates completely, the singularity also disappears? Maybe information is encoded in subtle correlations of radiation that we simply do not know how to calculate. Maybe it leaks through some quantum channel we do not know about. Hawking stubbornly held his position, but in 2004, he publicly admitted he was wrong. He made a bet with other physicists and lost it. Information, he stated, is nevertheless preserved. It comes back out along with the radiation, but so subtly encoded that we cannot read it with our methods. This was a dramatic admission. One of the greatest minds of the 20th century publicly admitted an error. But the question is not solved to this day. We do not know exactly how information comes out. We do not know the mechanism. Different theories propose different answers, and some of these answers turn our understanding of reality upside down. One of the most radical ideas is the holographic principle. It states that all information about a three-dimensional volume of space can be encoded on its two-dimensional surface. Like a hologram on a credit card contains a three-dimensional image, although it is flat itself? This sounds like a technical trick, but in fact, it is a statement about the nature of reality. Maybe our universe is a hologram? Maybe everything we consider three-dimensional is actually two-dimensional information projected onto a distant boundary of space. This idea was born from the analysis of black holes. Physicist Jacob Bekenstein showed that the entropy of a black hole, a measure of disorder, a measure of information, is proportional to the area of its event horizon, not its volume. This is strange. Usually, the amount of information that can be packed into a system grows with volume. More space, more room for data. But for a black hole, this is not so. All information lives on the surface. The event horizon acts as a screen on which everything that ever fell inside is recorded. And this idea turned out to be much broader than just black holes. It can describe the entire universe. According to the holographic principle, the three-dimensional space in which we live may be an illusion. Fundamental reality is a two-dimensional surface very far on the boundary of the observable universe. Everything that happens here, stars, planets, people, thoughts, is a projection of information from that surface. We are shadows on the wall of Plato's cave. But in a literal sense, this is not a metaphor. This is a mathematical theory that serious physicists study. And it works. It solves certain problems of quantum gravity. It explains how information cannot be lost in a black hole because it was never actually inside. It always remained on the horizon, on the surface. Falling into a hole is an illusion of a three-dimensional projection. In two-dimensional reality, nothing falls anywhere. Everything remains on the boundary. But this idea creates new problems. If information remains on the horizon, what does the astronaut who falls into the hole feel? He crosses the horizon and flies inward. For him, the horizon is empty space. No wall, no screen. But if all information about him remains on the horizon, does this mean that two copies of the astronaut exist? One on the surface of the horizon, encoded in quantum fluctuations, the other inside, flying toward the singularity. This violates another fundamental principle of quantum mechanics, the no-cloning theorem. You cannot copy a quantum state. This is a proven theorem. But a black hole seems to do exactly that. One astronaut on the horizon, another inside. A copy is forbidden, but it exists. A paradox. In 2012, a group of physicists proposed a radical solution. They said, maybe there is no copy. Maybe the astronaut does not cross the horizon painlessly. Maybe at the horizon, a wall of fire, a firewall, a barrier of high-energy particles awaits him, which will burn him instantly. This contradicts general relativity, which says that the horizon is locally indistinguishable from empty space. But if we take quantum mechanics, information conservation, and the no-cloning theorem seriously, then a firewall is inevitable. This is the price for consistency. Either we sacrifice the principles of quantum mechanics, or we sacrifice the principles of general relativity. There is no third option. The firewall idea caused a storm in the scientific community. It was a challenge to basic concepts. If a firewall exists, then the event horizon is not a harmless geometric boundary. It is a physical surface, a place of real processes, a place where quantum effects become macroscopic. But where does this fire come from? One of the answers is related to quantum entanglement. When a black hole evaporates, each pair of Hawking radiation particles is entangled. One particle flies off into space, the other falls into the hole. They are connected by quantum correlation, but if information must come out, then the radiation particles must be entangled not only with each other, but also with the inner part of the whole. And this means that one particle is entangled with two systems at once. Such double entanglement violates the rules of quantum mechanics. You cannot entangle one qubit with two different qubits simultaneously. There is one way out. Break one of the entanglements. And if the connection between the outgoing particle and the falling one breaks, then this connection releases energy, huge energy. The event horizon turns into a boiling cauldron of quantum activity. Particles are born and annihilate, creating intense radiation. Firewall. Any object that tries to cross the horizon will be torn by radiation into elementary particles before it even touches the boundary. There will be no smooth crossing. There will be no journey inside, only instant incineration. This is a cruel option, but it saves quantum mechanics. Information is not copied, not cloned. It remains on the horizon because nothing passes inside. Everything burns at the boundary. A black hole turns out not to be a prison, but a furnace. Entering it is fatal not because you cannot get out of it, but because you cannot reach it. But this raises a new question. If a firewall is real, why do we not see its effects? Why do stars calmly fall into supermassive black holes in the centers of galaxies? Why are there no signs of monstrous radiation at the horizons? Maybe the firewall arises only in the late stages of whole evaporation, when it is already old and small. Maybe it is connected not with the horizon itself, but with information saturation. A hole can safely absorb matter up to a certain limit, and then something breaks. We do not know. It is impossible to check these ideas experimentally. We cannot fly to a black hole and see if there is a firewall there. This is a purely theoretical battle, but the stakes are huge. The answer depends on which of our fundamental theories survives and which turns out to be incomplete. Another idea that tries to save the situation is wormholes. Maybe the inner part of a black hole is connected to another region of space-time through a tunnel. Maybe the singularity is not the end, but a transition. You fall into a hole on one side and fly out somewhere else or at another time. This is a classic idea of science fiction, but the mathematics of general relativity allows such solutions. Einstein's equations allow the existence of wormholes, bridges between different points of space-time. The problem is that these solutions are unstable. For a wormhole not to collapse, exotic matter with negative energy is needed. Such matter violates standard energy conditions. We have never observed it. We do not know if it can exist. But even if wormholes are possible, they do not necessarily solve the information paradox. If information goes through a wormhole to another place, it is still lost to our universe. We cannot return it. It is like throwing a letter into a portal that leads to a parallel reality. The letter is not destroyed, but for you, it has disappeared forever. Although there is a more subtle version of the idea. Maybe a wormhole connects the inner part of a black hole with its own radiation. Information that falls inside is somehow transmitted through a quantum bridge to the Hawking particles that fly away. This is called the ER equals EPR idea, that gravitational wormholes of Einstein-Rosen are equivalent to quantum entanglement of Einstein-Podolsky-Rosen. Sounds like a play on words, but it is a serious hypothesis. It was proposed by Juan Maldacena and Leonard Susskind. The essence is that entanglement between particles is not just an abstract quantum correlation, it is a real geometric connection, a tiny wormhole in the fabric of space-time. Two entangled particles are connected by an invisible bridge. And if this is so, then the black hole and its radiation are also connected. Information is not lost, it flows through entanglement. It is encoded in the structure of quantum correlations between the inner part of the hole and the outgoing photons. This is an elegant solution. It combines quantum mechanics and gravity. It preserves information. It makes the universe consistent. But this is still a hypothesis. Mathematical details are devilishly complex, and there is no way to check this directly. So what happens when an object falls into a black hole? Let us try to put all the pieces together. You approach the event horizon. For an external observer, your time slows down. You turn red, dim, and freeze at the boundary forever. Your information is smeared over the surface of the horizon. It is encoded in quantum fluctuations. When the hole evaporates, this information is gradually released with Hawking radiation. The process takes an incredibly long time, but in the end, everything comes back out. Quantum mechanics triumphs, information is preserved. But from your own point of view, the story is completely different. You cross the horizon. Maybe you pass through a firewall and evaporate instantly. Maybe not, and you calmly fly further toward the singularity. Tidal forces build up. Your body stretches, tears, turns into a stream of atoms. You reach the center, and here our physics breaks. What happens in the singularity, no one knows. Maybe their quantum effects smooth out the infinity. Maybe space-time becomes discrete, grainy, and the singularity turns out to be just a very small region with huge but finite curvature. Maybe a wormhole opens, and you fall into another universe or into another era of our universe. Maybe time and space finally swap roles, and the concept of movement loses meaning. We do not know, and perhaps we'll never know, because everything that happens there is hidden from us by the horizon. The cosmic censorship principle protects the universe from the chaos of the singularity. But what happens to you, the falling observer? For you, the events are real. You experience them. Where is your story recorded? This brings us back to the observer's paradox. Two stories, two realities. One outside, one inside. And both are true. Maybe the question is not what happens in reality, but for whom it happens. Maybe reality is not absolute, it depends on the observer. This is not a new idea. Quantum mechanics has long been telling us that measurement changes the state of the system. The observer is not passive, he participates in the creation of reality. But black holes take this idea to the extreme. Not just measurement, but the very existence of events becomes relative. For one observer, an event occurs. For another, it does not. And there is no way to reconcile these two views, because information cannot travel from under the horizon. Two branches of reality are forever separated. This may seem like a philosophical trick, but it is a physical problem. It calls into question the very concept of objective reality. If events depend on the observer, what remains of the idea of a single universe? Maybe the universe is not a single monolith, but a mosaic of local realities that intersect and overlap, but never fully merge. Each observer carries his version of the story. These versions are consistent locally, but may diverge globally. Black holes are places where divergence becomes absolute, where two branches of reality are finally separated. And there is no God observer who would see both stories simultaneously. There is no absolute point of view. There are only local observers and their limited perspectives. If this is true, then black holes teach us something fundamental about the nature of knowledge. We live in a world where not everything is knowable. There are boundaries beyond which we cannot look even in principle. The event horizon is not just a physical barrier, it is an epistemological barrier, the boundary of knowledge. Beyond it lies territory about which we can build theories, but will never check them. We can argue whether there is a firewall or a wormhole there, but we can never send a probe and look. The probe will cross the horizon and fall silent forever. It will not be able to transmit data to us. We will remain outside with our guesses and equations. And this is normal. This is part of the game. The universe is not obliged to reveal all its secrets. But this does not mean that we should stop researching. On the contrary, it is precisely the riddles of black holes that push us toward new ideas. They force us to rethink basic concepts: space, time, information, reality. Each attempt to resolve a paradox gives birth to a new theory: the holographic principle, the firewall, wormholes, quantum entanglement as geometry. All these are the fruits of the struggle with black holes. And these ideas are applicable not only to holes. They can explain the structure of the entire universe. They can lead us to a unified theory of everything. Black holes are a laboratory for checking the most radical hypotheses, a place where the laws of nature are pushed to the limit, where classical physics ends and quantum gravity begins. And one more point. Black holes are not just exotic objects somewhere far away. They play an important role in the evolution of the universe. Supermassive black holes in the centers of galaxies regulate star formation. When a hole is active, when gas falls onto it, this process releases huge energy. Jets, streams of particles flying out from the vicinity of the hole at speeds close to the speed of light. These jets heat the surrounding gas, disperse it, preventing it from cooling and collapsing into new stars. The hole slows down the growth of the galaxy. It controls its fate. Without black holes, galaxies would look different. Maybe there would be more stars in them. Maybe fewer heavy elements. Maybe the conditions for life would be different. Black holes are woven into cosmic ecology. Moreover, black hole mergers are some of the most powerful events in the universe. When two holes collide and merge, they emit gravitational waves, ripples in the fabric of space-time. These waves carry information about the event. They travel through space at the speed of light, and recently we have learned to detect them. The laser interferometers LIGO and Virgo have recorded dozens of such events. We literally hear black holes, hear their last dance before merging. The frequency of the signal grows like the tone of a whistling shell. Then a sharp surge, the moment of contact, and silence. A new hole, calm and symmetrical. These signals give us direct information about the properties of black holes. We can measure their masses, angular momenta, check if they are indeed described by Einstein's solutions. So far, everything matches. Black holes behave exactly as general relativity predicts. But the most exciting part is still ahead. We are only beginning to study black holes. New telescopes, such as the Event Horizon Telescope, take pictures of the shadow of black holes, the silhouettes they cast against the background of glowing gas. We see the shape of the horizon. We see how it distorts light. We can compare these observations with theoretical predictions. This is an unprecedented test of general relativity in extreme conditions. And so far, Einstein is winning. But if we find a deviation, it will be a revolution. It will be a sign that new physics is needed, that something we do not understand is happening beyond the horizon. There are also more speculative ideas. Some physicists suggest that black holes may be gateways to other universes, that within each hole a new cosmos is born, that our universe itself may be inside a black hole of a larger universe. This is the multiverse hypothesis, taken to the extreme. It is untestable, but mathematically elegant. It explains why our universe is tuned so precisely that life is possible in it. Maybe there exists an infinite network of universes born from black holes, each with its own laws of physics, its own constants. We live in one of them, the one where conditions are right for us. This is natural selection. On a cosmic level, those universes survive that produce many black holes. And black holes form in galaxies with stars, and stars require certain conditions. The circle closes. But these are all speculations, beautiful but unprovable. Let us return to what we know for sure. Black holes exist. They form during the collapse of massive stars. They radiate, they evaporate, they create paradoxes that do not fit into any of our theories. And that is exactly why they are so valuable. They point to the boundaries of our understanding. They tell us where we need to dig deeper, where we need to look for new physics. Maybe the answer is in string theory, maybe in loop quantum gravity, maybe in something completely new that we have not thought of yet. But the path lies through black holes, through their paradoxes and strangeness. And there is something poetic in how this problem is arranged. Black holes are places of maximum entropy, maximum disorder, a pit that absorbs everything. But they are exactly what force us to create the most ordered, precise, deep theories. We oppose the chaos of the whole with the order of our mind. We try to understand the incomprehensible. This is the quintessence of the scientific enterprise. We cannot go in there. We cannot touch the singularity, but we can think about it. We can build models, make predictions, look for indirect confirmations. And in this process, we learn not only about black holes, we learn about ourselves, about the possibilities of the human mind, about how far abstract thinking can go. Black holes remind us that the universe is not obliged to be convenient for understanding. It does not adapt to our intuitions. It does not care about making us feel comfortable. It just exists with all its strangeness and paradoxes. And our task is to accept this strangeness, not to try to squeeze nature into the framework of habitual experience, but to expand the framework of our experience to accommodate nature. This requires humility, the recognition that we can be wrong, that our theories are not complete, that there are still many mysteries ahead. But it also requires courage. The courage to look into the abyss and not turn away. The courage to ask questions for which there are no easy answers. The courage to accept that some questions may remain open for a very long time, maybe forever. And yet we continue. We continue to build detectors, launch telescopes, calculate equations. We continue to argue about firewalls and holograms because that is what we do. This is our nature. We are curious monkeys who look at the stars and try to understand how it all works. And sometimes we find answers. Sometimes the puzzle pieces fit together, and then the world becomes a little more understandable, a little more ordered, a little less frightening. But with every answer, new questions appear. With every step forward, we see how the horizon of the unknown expands. And that is normal. This is part of the path. This is a sign that we are moving in the right direction. Black holes are a mirror in which we see the reflection of the fundamental problems of physics, the problem of unifying quantum mechanics and gravity, the problem of the nature of space and time, the problems of information and causality. All this rests on black holes. They are the knot where all threads converge. And untying this knot could lead to a breakthrough, to a new understanding of reality, to a theory that will combine everything we know into a single picture. This is the goal toward which physics strives, and black holes are one of the keys to this goal, perhaps the most important key. But let us not forget about the practical side. Black holes affect us directly, not in the sense that we will fall into one of them. The chance of that is negligible, but in the sense that they formed the conditions in which we appeared. The heavy elements that our bodies consist of, carbon, oxygen, iron, were born in stars. And the fate of stars is connected with black holes. Without black holes, galaxies would evolve differently. Star formation would have followed a different scenario. Maybe it would have been harder for life to arise, maybe easier, we do not know. But there is a connection. We are children of stars, and stars are connected with holes. This is part of a large cosmic cycle: birth, life, death, rebirth. Black holes are the grave diggers of stars, but they are also the sculptors of galaxies. They create the conditions for new generations of luminaries. And one more point worth mentioning. The study of black holes has led to the development of many technologies and methods. Gravitational wave astronomy is a new field that opened only a few years ago. We learned to build detectors capable of recording space fluctuations smaller than the diameter of a proton. This is a triumph of engineering and physics. These technologies will find application in other areas as well. Precise measurement, signal processing, noise filtering. All this will come in handy. In addition, theoretical developments in the field of quantum gravity and information theory could lead to breakthroughs in quantum computing, cryptography, materials science. Fundamental science always pays off. Maybe not immediately, maybe not in an obvious way, but it pays off. Now let us try to summarize some results and look at the whole picture as a whole. Black holes began as a mathematical curiosity, a strange solution to Einstein's equation. A solution that Einstein himself did not want to accept, but reality turned out to be richer than fantasies. Black holes exist. We see their effects. We hear their gravitational songs. We photograph their shadows. They are real, like planets and stars. But they are not just another kind of astronomical object. They are a rift in the fabric of reality, a place where our theories break, where paradoxes arise that require a new understanding. We learned that information is not an abstract concept. It is a physical quantity, as fundamental as energy or momentum, and it cannot disappear. This is a requirement of quantum mechanics. But black holes seem to violate this rule. Do they destroy information or not? Maybe information is preserved, but so cleverly encoded that we do not see exactly how. Maybe it stays on the horizon. Maybe it leaks through quantum channels. Maybe the horizon itself is a hologram on which the entire history of the fall is recorded. These ideas led us to the holographic principle, a revolutionary concept that says our three-dimensional universe may be a projection of two-dimensional information, that depth is an illusion, that everything we see, feel, know is shadows on the wall, encoded data deployed in space. If this is true, then the consequences are dizzying. This means that fundamental reality is arranged not at all as it seems to us, that space is not a basic concept, but a derivative, that it arises from the entanglement of quantum states, that geometry is a code. This makes the universe look like a computer simulation, not in the sense that someone is simulating us, but in the sense that reality at a fundamental level is the processing of information. The laws of physics are algorithms. Particles are bits. Interaction is calculation. And in this picture, a black hole is an area where the calculation becomes maximally intensive, where every square centimeter of the horizon stores a huge amount of information, where encoding and decoding reach the limit. But let us return to the firewall idea. If it is real, then a journey into a black hole is impossible. Not because you cannot return, but because you cannot enter. The horizon becomes a barrier of fire that incinerates everything on approach. This is a radical idea. It violates the equivalence principle, one of the pillars of general relativity. The principle states that locally in free fall you do not feel gravity. For an astronaut falling into a hole, the horizon should be indistinguishable from empty space. But if there is a firewall there, then the principle is violated. The astronaut burns up. He feels something very real. This means that either quantum mechanics is incorrect or general relativity is incomplete. One of the two great theories must fall, or both, and in their place, a new theory must appear that will combine them without contradictions. This new theory is quantum gravity, the holy grail of modern physics. We have been looking for it for decades. String theory is one of the candidates. It says that on the Planck scale at distances of the order of 10 to the power of -35 meters, space-time stops being smooth. It becomes foamy, quantum. Particles are not points, but tiny oscillating strings. Different modes of vibration correspond to different particles. The graviton is one of the modes, so gravity is included in the quantum picture. String theory predicts additional dimensions of space, 6 or 7 dimensions curled into tiny forms, invisible on our scales. This sounds wild, but the math works. String theory solves some problems of quantum gravity. It gives finite answers where other theories give infinities, but it has no experimental confirmation. The energies needed to test its predictions are unattainable. This is disappointing, but it does not stop research. The alternative is loop quantum gravity. It does not introduce strings, it quantizes space-time itself. It says that space consists of discrete pieces, atoms of space, spin networks, graphs whose nodes represent quanta of volume and edges quanta of area. In this picture, there is no smooth continuum, there is only a discrete structure. And at this level, Black hole singularities may disappear. Infinite density is replaced by very high but finite density. Collapse stops at the Planck density. Inside the hole, not a singularity is formed, but a bounce. Matter shrinks to the limit and then bounces back, possibly forming a new expanding universe. This is called a black hole as a white hole. A black hole absorbs matter from one side, a white hole throws it out from the other. Between them is a quantum transition. This is speculative, but beautiful. Both theories, strings, and loops try to solve one problem: how to make gravity quantum, how to get rid of infinities, how to understand what happens in singularities. So far, neither of them has won. Maybe the truth is somewhere in the middle? Maybe a third idea is needed? Maybe we are not yet ready for the answer? Maybe new mathematical tools, new concepts, a new language are needed. Physics is full of such moments when the old language turns out to be insufficient and a new one needs to be invented. Newton invented calculus to describe motion. Einstein used Riemannian geometry to describe gravity. Maybe for quantum gravity, something even more abstract is needed. And at the center of all these efforts stand black holes. They are a testing ground. If your theory cannot explain black holes, it is not complete. If it cannot resolve the information paradox, it is not correct. Black holes set the bar, they set the standard, and that is fair because they are the most extreme objects we know. If a theory works for black holes, it probably works everywhere. This is a criterion of truth. This is a test that needs to be passed, and so far, no theory has passed it completely. But we are close. We are on the threshold. Maybe in the coming decades we will see a breakthrough. Maybe one of the young physicists reading these lines will take the decisive step, find the missing piece, connect everything together. And now let us look at the philosophical side. What do black holes tell us about our place in the universe, about the nature of knowledge, about the limits of cognition? The event horizon is not just a physical boundary, it is an epistemological boundary. Beyond it lies a region about which we, in principle, cannot obtain information. This is not a question of technology, it is a fundamental limitation. Even if we had infinite resources, we could not find out what is happening inside the horizon. Information does not exit. This is the definition. And this means that there are questions to which we will never get empirical answers. We can build theories, we can make assumptions, but we cannot check them directly. This is the limit of science, and that is normal. Science does not claim to know everything. It claims to know what can be checked. The rest is the area of philosophy, speculation, faith. But there is another side. The event horizon is also a metaphor for the boundaries of our understanding. Each era has its horizons, something beyond which it cannot look. The ancients could not imagine that the earth was round. The medievals could not imagine bacteria. People of the 19th century could not understand relativity. Each time the horizon moved, we learned more, we looked further, but there was always a new horizon, a new boundary of ignorance. Black holes are the horizon of our time, the place where our understanding ends. But this is not a reason for despair, it is a reason for inspiration, because boundaries are created to be overcome. We cannot physically look inside a black hole, but we can look inside mathematics, we can explore equations, we can build models, and sometimes models turn out to be good enough to give us understanding, even without direct observation. Black holes also remind us of the fragility of knowledge. All our science is built on observations. We look, measure, draw conclusions. But observations are always limited by our position. We are observers on the outside. We cannot be inside and outside simultaneously. And this creates an asymmetry. We see one side of the coin, the other side is hidden. And maybe it is arranged completely differently. Maybe other laws operate inside a black hole. Maybe time flows backward there. Maybe universes are born there. We do not know. And this uncertainty is part of the human condition. We live in a world that is bigger, stranger, deeper than we can comprehend. And this is simultaneously frightening and fascinating. Frightening because we lose the illusion of control. Fascinating because an infinity opens before us. And one more point. Black holes are a symbol of inevitability, of a fate that cannot be changed. Inside the horizon, your future is determined. You will fall into the singularity. This is written in the geometry. There is no choice, no free will. This is determinism in its pure form. But paradoxically, it is precisely this determinism that gives birth to freedom. For an external observer, your fall never ends. You freeze at the horizon, smear in time, become eternal. Two fates, two stories. One deterministic, the other open. And both are true. This can serve as a metaphor for human life. On the one hand, we are all moving toward an inevitable end. Death is our personal singularity. We cannot avoid it. On the other hand, while we live, while we are outside this final horizon, we are free to choose. Our stories are open. We write them with our actions, and even after death for those who remain, we remain in their memory, in their time. We are smeared in their perception, like an object falling into a hole is smeared for an external observer. This is, of course, poetry, not physics, but poetry is also important. It helps us comprehend abstract ideas, give them a human dimension, connect with our experience. And in this sense, black holes are not only an object of scientific research, they are also an object of reflection. A reason to think about time, fate, knowledge, reality. About what it means to be an observer in this strange and beautiful universe. About how we are connected with the cosmos. We are part of the same fabric. The same laws that govern black holes govern the atoms of our body. The same gravity that curves space around a hole holds us on the ground. The same quantum mechanics that creates paradoxes on the horizon creates chemistry, life, consciousness. We are not separated from the universe, we are part of it. We are the way in which the universe knows itself. And when we study black holes, we study ourselves, the limits of our understanding, the possibilities of our mind, the ability to abstract, generalize, predict, the ability to look at the world and see depth behind the surface, behind chaos, order, behind randomness, law. This is a unique human trait. We can ask questions about the nature of reality, and we can find answers. Not always, not immediately, but we can. And this makes us special. Not in the sense that we are the center of the universe. We are not the center. We are a tiny speck on the outskirts of one of billions of galaxies. But we are a speck that thinks, that asks questions, that builds telescopes and accelerators, launches probes and satellites, writes equations and checks hypotheses, that looks into the sky and sees not just points of light, but worlds, stories, laws. This is a miracle, and it is worthy of respect. Black holes teach us humility. They show how much we still do not know, how much is yet to be discovered. They put us in our place, remind us that the universe is not obliged to be understandable, that our intuitions developed in the African savanna are not always applicable to the extreme conditions of space, that sometimes you need to let go of familiar concepts and accept a new picture, even if it seems insane. This is exactly how science develops. Through overcoming old dogmas, through accepting the new, through readiness to be wrong and learn from mistakes. Einstein did not believe in black holes, but they turned out to be real. Hawking believed that information was destroyed, but admitted an error. This is not a weakness, it is a strength, the ability to change an opinion in the face of new data. This is the essence of the scientific method. And in this sense, black holes are not enemies. They are not a threat. They are teachers. They ask us the most difficult questions. They check our theories for strength. They force us to be better, to think deeper, to calculate more precisely, to check more thoroughly. And in the process, we become smarter, our theories become more powerful, our understanding wider. This is an infinite cycle. Each answer gives birth to new questions. Each solution opens new problems. And that is beautiful, because it means the journey never ends. There is always something to discover. There is always somewhere to move. The horizon recedes, but does not disappear. And we continue to go toward it because that is who we are. Researchers, pioneers, dreamers who look at the stars and ask, why, how, what if? So what is a black hole in the final analysis? It is a rift in the fabric of reality, a place where space and time stop behaving in a familiar way, where the laws of physics are pushed to the limit, where quantum mechanics meets gravity and a war begins between them. It is a laboratory of nature where the most fundamental ideas are checked. It is a mirror in which we see the boundaries of our knowledge. It is a teacher who asks the most difficult questions. It is a symbol of inevitability and mystery. It is the poetry of mathematics. It is a challenge to the human mind. And it is a real physical object that exists there in space, indifferent to our theories and disputes. Black holes do not know about our paradoxes. They just exist. They do what they do. They curve space, absorb matter, radiate, evaporate. And we observe, measure, think, argue, try to understand. And sometimes it seems to us that we are close, that a little more, and everything will become clear. And then a new experiment appears, a new observation, a new idea, and the picture becomes complicated again. And we start over. We build new models, check new hypotheses, look for new answers. And so it will continue, maybe forever, maybe as long as science exists, as long as there are people who look into the sky and ask the question, what is there beyond the horizon? We began with the fact that black holes are not what they seem. They are not black, they are not holes. Now we know why they radiate, which means they are not quite black. They are not empty. Their horizon encodes information. They are not just objects in space. They create space around themselves. They are not just points on the map of the cosmos. They are nodes in the network of causality. Places where the past meets the future, where the inner is separated from the outer forever, where stories diverge and never connect again. This is deeper than just an astronomical phenomenon. This is a philosophical problem. This is an existential question. What happens when you cross a boundary from which there is no return? What does it mean to be cut off from the rest of the universe? What does it mean to move in a direction from which there is no exit? This may seem gloomy, but there is another view. Maybe a new journey begins inside the hole, a new reality, new laws. We do not know, and maybe we'll never know, but we can dream, we can imagine, we can build theories and hope that one day we will find a way to check them or at least understand deeper. And in conclusion, I want to say, black holes are a gift of nature to science. They give us a testing ground for checking the boldest ideas. They force us to go beyond the limits of comfort. They do not let us rest. They say, you have not understood everything yet. Dig deeper, think wider, be bolder. And we dig, and we think, and we discover. Not always what we were looking for. Sometimes something completely unexpected. The holographic principle was born from attempts to understand black holes. Quantum entanglement as geometry, too. These ideas are now applied far beyond the boundaries of black holes. They change our understanding of quantum field theory, string theory, cosmology. They open new directions of research. This is a domino effect. One idea launches another. One discovery leads to the next. And in the center of this cascade stand black holes, catalysts of thought, generators of questions, sources of inspiration. So look into the sky. Look for black holes, not in telescopes, although that too is beautiful. Look for them in equations, in thought experiments, in philosophical dialogues, in attempts to understand how the world is arranged at the deepest level. Black holes wait there in the darkness of space. silent, mysterious, incomprehensible. They will not reveal their secrets easily, but they do not hide them intentionally either. They just exist. And our task is to decipher their language, to understand their message, to hear what they are trying to tell us. And what they tell us is this: reality is stranger than you think. It is deeper than you can imagine. It is full of paradoxes and miracles, and it waits for you to explore it. So do not stop. Do not give up. Continue to ask questions. Continue to look for answers, because that is exactly what makes us humans. That is exactly what gives meaning to our existence. We are beings who look into the abyss, and the abyss looks back. And in this look, knowledge is born, understanding is born, a connection between us and the cosmos is born, a connection that makes us part of something bigger, part of the great cosmic dance, the dance of matter and energy, space and time, order and chaos. And black holes are some of the most fascinating dancers in this ballet. They do not just destroy, they also create. They do not just absorb, they also radiate. They do not just hide, they also reveal. They reveal the nature of reality. They reveal the limits of knowledge. They reveal the possibilities of the mind. And for this, we should be grateful to them, because without black holes, our picture of the world would be poorer, our theories weaker, our curiosity less sharp. Black holes wake up in us the researcher, the philosopher, the poet. They force us to look deeper, to think wider, to feel fuller. And this is perhaps their most valuable contribution, not to the treasury of knowledge, but to the treasury of experience, the experience of meeting the unknown, and the experience of pride that we, small beings on a small planet, can at least try to understand these colossal, incomprehensible, beautiful monsters. Black holes. It is a shadow from the abyss, but light is hidden in this shadow, the light of understanding. And we will look for it again and again until we find it, or until we realize that looking is already enough in itself. If you like this journey into the heart of darkness, support the channel with a like and a subscription. We will continue to explore the deepest mysteries of space. There are still many questions ahead for which there are no easy answers, but that is exactly what makes them interesting. Thank you for being with us. And remember, when you look into the night sky, somewhere there, in the darkness between the stars, black holes are hidden. They wait, they are silent, but they are there. And one day we will understand them fully until the end, or at least a little better than today, and that will already be a victory.